Hello, I'm Sophie Rovner from the American Chemical Society. Welcome to this news briefing from ACS's 256th National Meeting and Exposition in Boston. We're joined today by Professor Eleanor Schofield from the Mary Rose Trust. She will discuss a new approach to conserving salvaged wooden ships and artifacts with smart nanotech. Professor Schofield.
Good morning, everyone. I'm here today to talk about a collaboration between the Mary Rose Trust, where I work, the Core Research Group at the University of Glasgow, and the O'Reilly Research Group at the University of Birmingham. The Mary Rose is a 16th century warship. It was commissioned by Henry VIII. It sailed for many years before tragically sinking in 1545. The ship remained under the seabed for hundreds of years and then was salvaged in 1982 and now is in a purpose-built museum in Portsmouth, UK. Alongside the ship, we have thousands of artifacts, and we use this to tell the story of the ship and also of all the people that were on board. A lot of the collection is made of wood, and whilst the wood is in really good condition for everything it's been through and for the environment it's been subjected to, it has degraded. So when it comes out of the water and it's wet, we can't just let it dry. We have to treat it, and we have to replace some of the degraded wood components. And we use polyethylene glycol, or PEG as we call this, to do that. So we replace some of the lost wood components, so then when we dry it, it has some structural stability, it's not going to shrink and crack. Now, when we come to dry it, we have to be conscious of some other problems. Due to the wood being under the seabed for so long, it has foreign species lodged in it, such as sulfur and iron. The sulfur comes from the seawater, and the iron comes from, well, it's in the seawater, but also predominantly from corroded fixtures and artifacts that haven't survived that environment. If we just move the slide along one. Basically what can happen is you get these iron-sulfur compounds within the wood, and when they're exposed to oxygen, so when we're drying it, it can rapidly oxidize and form sulfate salts and sulfuric acid, which can be very damaging. This is kind of what they can look like on the artifacts. So they don't look very good, but also they're very acidic. We've tried different treatments before to try and neutralize this, but this usually ends up with the material remaining within the wood, which is not ideal. And this is how this project has come about. So if we move on to the next slide. What we've been doing is taking magnetic nanoparticles and functionalizing them. So we're adding on receptors which will capture iron. The reason we've used magnetic nanoparticles is it means that we can drive the treatment in, but also we can drive it out and get those things out of the wood. In addition to the functionalized nanoparticles, we've then embedded them in a thermoresponsive polymer. So that means that above a certain temperature, the polymer is a gel. Once we go below a certain temperature, it then turns to a liquid, so then it can drive the treatment into the wood. And then when we're confident it's complete, we can apply a magnetic field to pull the particles out, raise the temperature so it forms into a gel again, and then we can peel it off the surface of the wood. So one of the things that's really, really important to us is that we're not damaging the wood. It has to be friendly to the wood. So we've tested the particles in a solution of iron, so we know that the chemistry is working and it can sequester the iron. We've tried it on simulated wood, so what I mean by that is that we've taken fresh wood and we've soaked it in iron sulfate, so we know that it's got lots of iron in there for this treatment to try and capture, and we've shown that it's worked. And the next step, we'll be moving on to the actual artifacts. This should be easier in some ways because the wood is degraded. It means that there are wider, more integrated pathways to get the treatment in. So it's really exciting for the wood, but more than that, it's the concept that's really exciting, because once we show that the technology can work, we can then tailor it to some of the other materials, because basically one of the big problems for us with everything is these artifacts have been soaking and marinating in the seawater for years and years and years. So there's all kinds of things in there. So once we get the technology working, we can then try and look at different agents to sequester different particles. So that's an overview of where we're at.
All right, thank you very much. Now we would like to open this to questions, and if you have a question, please state your name and affiliation before asking it.
Hello, so it's Cathode Recycle from Chemistry and Industry magazine. What ligands are you using to attach to the magnetic nanoparticles to actually extract the iron?
We're using porphyrin and also DTPA. We've done most of our work on the porphyrin at the moment, so that attracts the iron. And the DTPA we have used before, actually. That's quite commonly used on artifacts just by putting it into solution and letting it kind of leach out. But what we're looking at more is trying to do localized treatments, so things that maybe have already been consolidated. What DTPA has been used for before is things before they've been consolidated with PEG, so you can kind of submerge it. But once you've kind of gone down this route and conserved them, and they're, say, on display in the museum, you can't very readily take them back out and put them into solution.
What is DTPA?
Yeah, that's one I probably can't say off the. It's a pentoic acid, but the beginning bit I don't know off the top of my head.
And you mentioned the first thing will be to try them on some artifacts. Do you have sort of what kinds of objects will you try it out on?
So we have lots of samples. We have core samples from the ship. So these are. They're about 5 millimeters in diameter. The length is anywhere between kind of 10 and 20 centimeters. We literally bore them out to be able to analyze them. So they're quite good candidates because they've already been taken from the ship. They can't be used for something else. We also have quite a lot of timbers which either have not been conserved or they're unidentified. We've had various curators look at them. We don't know what they are, or they're the parts that have over the years maybe become separated. So we have quite a lot of bits that we can test on before we went anywhere near a kind of complete artifact. I mean, this is a lot of what we do, why we do these steps and try to simulate the wood, because whilst it isn't exactly the same, we want to make sure that we've tested every possible thing before we go anywhere near our collection.
And how much can you extract? You said, one of the advantages is that you can actually remove this material as well by peeling it off. I mean, is it 100% removal? Can you get rid of all of it? And similarly, how much of the acids can you remove as well?
It's a really difficult one to answer because a lot of the time, especially when it comes to an artifact, you don't know what's in there because you're not going to kind of do cross sections of it because you can't. So you can kind of measure what's on the surface. I mean, it's definitely something that we'll move on to next. In the solution, which I can't remember the exact concentrations, but with the porphyrin, we were getting about 85% of the iron out of the solution. And that was within about 10 hours. I think if we'd gone for longer, potentially it could have taken more out. And it'll depend of the concentration of the porphyrin and how many possible locations there is for the iron to go. So I think it's certainly tailorable that within a set piece we could remove all of the iron.
And the thermoresponsive polymer, what temperature range? What's the sort of gel temperatures?
It's about 22 degrees. So the polymer to start off with, the polymer on its own is about 26 degrees, but once we add in these other components, it actually brings the temperature down, which works in our favour because we don't want it to be too high for the wood. We don't want to be subjecting it to too high a temperature. But around 22 degrees is perfect because we're not going to be stressing the wood at that temperature.
And just one last question, which was to ask about the acid deterioration. Can you say something about the actual process of that acid deterioration? I mean, with these sulfuric acid and the sulfates.
Yeah. So
and how much do you think this will slow that process down by?
So one of the there's been a lot of work done on monitoring this sulfur and seeing it evolve, but not so much on trying to quantify what's happened, what happens to the wood. And that's something that we've been trying to do since we started drying the ship in 2013, because in other studies it had more been retrospectively, they've been able to trace back the sulfur and see that it had evolved, whereas we were able to monitor it real time. This was actually a project with Diamond Light Source, the synchrotron in the UK. So we took samples from the wood. In fact, this is what a lot of the core samples were for, that we took them to the synchrotron and monitored the sulfur. So we've seen it evolving, and then we've also seen with using FTIR, we're able to look at, through that technique, you can look at the different components in the wood, and what happens is you see that the cellulose and the hemicellulose, they degrade first, so you have a much higher proportion of lignin to those in the degraded wood. And the point we've got to is that we can see where you've got concentrations of sulfur and iron, you can see that you have got a loss of cellulose and hemicellulose. And that's as far as we've got in terms of being able to quantify it. But that actually in itself is new, that's not been done before, so we're kind of trying to work through it as the ship dries.
Okay, thank you.
Thanks.
Pelo Buslig, ACS. What is the actual function of the magnetic nanoparticles to drag the particles inside the wood rather than vacuum infusion of the PEG? Because it's a fairly common practice to essentially take old pieces of wood and saturate them with polyethylene glycol and of various molecular weights, and it's functional. Is it to preserve the integrity, or is it easier on the porous part that's essentially lacking all the cellulose or hemicellulose there? Like what's other than, I noticed that you've got a magnet there kind of dragging the particles. Is that the only function, or is it something structural too?
So this is not in replace of treating with PEG, it's something complementary to it. So the PEG treatment is to go in and structurally stabilize the wood. So we have the situation where we have the ship, we have lots of artifacts which have been through this PEG treatment. As you say, it's very common to be done that way. But then after that, we see these iron and sulfur compounds forming. So we need something that can then get into the wood once it's already been PEG treated. So the function is to go in and try and take out the iron, because that is key to this oxidation process with the sulfur. So yeah, the primary purpose is to remove this iron and stop these acids forming which can degrade the wood.
Thank you.
This is Laura Cassidy with ACS, and I actually have two questions. First, how long do you anticipate it will take to apply the method over the entire ship and all of the artifacts?
It will never be our goal to do it over the entire ship for lots of different reasons. It's huge, it's 34 meters long, and it just wouldn't really be practical, and it probably doesn't need it. So one of the things with this is we're wanting to create something that we could apply in local areas, we're kind of equipping ourselves for the tools should we need them further down the line, because we know that it can happen. So it really will be reactive to when we see these salts forming, or if we know that there is some iron there. Sometimes it's not the salts, you can see kind of iron staining, so they would be brilliant candidates for us to think, right, well, that has the potential to form these acids, so let's get in there, put this patch on. Some of our galleries, the wooden artifacts, they range from obviously the ship, which is huge, then tiny little objects, but then you've also got really sizable gun carriages, which are in cases, so there is no way we are taking them out of the cases, right? So it's having something that the conservators could get in there and apply in situ. So it's more about making sure we have the necessary tools to deal with the problems as and when they rise.
Okay, got it. My second question was, how do you apply the external magnetic fields? And they're not as big as I was envisioning for the whole ship, but do you still need pretty large fields for the bigger artifacts?
At the moment, it has kind of just been tests with the magnet, and I'm not sure of the exact strength of it. This is our postdoc at Glasgow has been conducting these experiments, and it will vary obviously from the fresh wood to then the Mary Rose wood, because I think there'll be easier pathways in. You're trying it out on the hardest situation with fresh wood because it's really dense and there's not many pathways in. So that's kind of something more to be determined at this point.
Can you tell us a little more about the history of the ship itself and whether it's known why it sank?
So the ship was commissioned in 1509 when Henry VIII first came to the throne. He was really kind of flexing his muscles, preparing himself for what was to come. It sailed for many years, was in numerous battles, and it met its end in the Battle of the Solent. So it was just off the English coast, so near where it is now. And it was an invading French fleet, which actually was bigger than the Spanish Armada that came years later. And the reason it sank, there are different theories, but the most commonly accepted one is that it had undergone lots of renovations mainly to equip it with more cannons to make it more powerful. And it meant that the waterline had raised quite significantly. And what happened on the day was that the ship turned quickly in bad weather, and they didn't shut the gun ports where they'd just fired in, so it meant that water came streaming in, and the ship, by all accounts, sank very quickly. And it was actually a huge tragedy. Over 500 people went down with the ship. And the way that ships would go into battle at that time is they'd go alongside each other and try to get on each other's ships. So they would have anti-boarding netting. But obviously in this situation, anybody that was below that was trapped on the ship as it went down. And they did try and salvage some parts of it to start with, but with very limited success. And there were some attempts again in the in the 1800s, a pair of brothers, the Dean brothers, they pioneered what we now think of as scuba diving gear. They went down and got some items from it, and then it remained down there, and actually was harder to discover. But the reason we have it is because it became covered in silt, so it was under meters of silt, and this is what preserved the wood. But yeah, made it a little harder to find when they did want to go and find it again.
Question in the back.
Katie Cottingham, ACS. So I was wondering, have you started to learn something about the time period and the people there by doing this preservation, or are you just kind of mostly focused on the preservation methods right now?
I personally am focused on the preservation methods, but my colleagues at the Mary Rose, they have done lots of work. It can sometimes overlap, particularly with one of my colleagues, Alexandra Hildred, some of the other projects I've got going on, looking at iron cannonballs. She's done a lot of research with them, so it can overlap. Sometimes we will be thinking, well, this one is degraded more than this one. Why is that? And she'll be able to help with where it was on the ship. There's all these kind of factors. So whilst it isn't my main focus, sometimes that will come in, and I love that. It makes it super interesting. But she does a lot of research into the artifacts, actually into the human remains as well. There's a lot of things going on with that now. So we've kind of scratched the surface of what we can learn about the materials and then about the story. And as the techniques that we use advance, it just means we learn more and more. So it's kind of a never-ending thing, really, which is wonderful.
Any further questions?
Thanks. Emma Stoy from Chemistry World magazine. You mentioned briefly that you might be thinking about using the same technique, but on kind of different materials or with slightly different functionalization on the nanoparticles. Could you tell me a bit about that?
Yeah, so basically pretty much everything that we have has something alien to it that you wouldn't normally find. Everything has salt in it, right, from the seawater. And so there's lots of different materials that we can test it on. The next step for us, first of all, with the wood, we've started with the iron because that's the kind of easier one to try and capture. It would be good to then try and find ways to capture the sulfur. But moving on to other materials, we have another project with Glasgow, again, chemistry, but also the Textile Conservation Centre there, starting to look at some of the other textiles that we have. So we have velvet, sailcloth, then moving also into things like leather, anchor cable, and they will all have kind of some of these species in them. So we'll be looking to try and tailor the treatment, whether it's the thing that we're trying to sequester, or whether the gel might need some moderating. I should have said before, actually, one of the other things that we'll be looking at is once we tried it on the wood and we see that we've removed the iron, the other thing will then be to kind of assess the wood. Is it okay? Has this changed it at all? So there's kind of like a full circle thing. And then if we start to look at other materials, it might be that potentially this is not quite right, so we'll need to tweak it. But it's kind of once we've got the concept going, we can then branch out into other things.
Thanks.
Any further questions? All right, well, thank you very much. Fascinating story. The archived version of this session will soon be posted at bit.ly/ACSLive_Boston 2018. Please join us for our next press conference at 9:30 a.m. today on how gut bacteria could provide the key to making universal blood. Thank you.